Force, Energy and Power, question 9. So, this time we have a nice topical rocket since NASA's finally getting back into the business of launching astronauts themselves instead of paying the Russians to do it for them. We've got a rocket that's got a mass of 4 times 10 to the 4 kilograms. Launched vertically upwards from the surface of the Earth, its engines produce a constant thrust of 7 times 10 to the 5 newtons. Draw a diagram showing all the forces acting on the rocket just after takeoff. Well, we've got the thrust upwards from the rocket motor, 7 times 10 to the 5 newtons. We've got the weight of the rocket downwards, which would be mass of the rocket times gravity, so 4 times 10 to the 4 times 9.8 should give you 392,000 newtons. In the real world, we've also got air resistance to worry about, but this isn't the real world, this is higher physics. And one of the nice things about higher physics is, unless they tell us we have to think about it, we get to ignore air resistance. Those of you that take advanced higher next year, not so lucky. On we go. Part 2, calculate the initial acceleration of the rocket. So, part 2, we need to find the unbalanced force. That is the 700,000 newtons from the rocket motor thrust minus the 392,000 newtons from the weight of the rocket gives us an unbalanced force of 308,000 newtons. And from that we can work out the acceleration F over m, 308,000 newtons unbalanced force over 4 times 10 to the 4 kilograms, which should give us an acceleration of 7.7 meters per second squared. For part B, as the rocket rises, the thrust remains constant, but the acceleration of the rocket increases. Give 3 reasons for this increase in acceleration. Well, there are 3 reasons, but they're all basically the same idea. As the rocket burns fuel, the mass of the rocket decreases, and as the mass of the rocket decreases, the weight of the rocket decreases, and as the weight of the rocket decreases, the unbalanced force increases, provided that, as it says in the question, the thrust from the rocket motor stays constant. Now, if we added in real-world stuff, we could also say things like air resistance decreases as it goes up through the atmosphere. And we could also say real-world things like dropping stages of the rocket once those bits have become empty of fuel. But as you can see, we're ignoring air resistance anyway. Dropping the stages that are empty of fuel, pretty much the same idea as burning the fuel. So the key, most important idea is the mass decreases, that means the weight decreases, that means the unbalanced force increases. And for part C of this question, explain in terms of Newton's laws of motion why a rocket can travel from the Earth to the Moon and for most of the journey not burn any fuel. Well, if it's not burning fuel, then there's no thrust from the motor, but it's in space. There's no resistance, so it's travelling at a constant velocity because there's no unbalanced force. So, as Newton 1 says, if there's no unbalanced force, then it continues with a uniform motion. The rocket was already in motion. Not putting any additional engine thrust on it simply means it doesn't accelerate. It doesn't mean it stops, it means it doesn't accelerate. We only need an unbalanced force for an acceleration. Something that's already moving, like a rocket on its way to the moon, can quite happily travel most of the way there without using any fuel at all, because for most of the way there, it's travelling at a constant velocity because there's no unbalanced forces acting on it.